Okay, so we have this function of x, and we're trying to get the arc length on the interval -1 to 1, and I made the function really crazy looking just because it's one of my favorite functions. It's called the Gaussian wave packet. And I talk a lot about these just because they're a really good illustration of how you can have an exponential function like modulating a trig function. So here's my trig wiggle, and then it's being crushed to 0 as I go to the left and right by this decaying exponential. So just a cool curve. And on this, you're asked just to set up the integral. And I asked you to perform the derivative inside the radical for the arc length formula. But after that, you're just stuck. There's no way to symbolically do the integral. And this is true for a lot of arc length integrals. They just require numerical approximations because the formula is just so nasty. So our arc length formula is that I take the integral from the first value of x to the last, so -1 to 1, square root 1 plus f prime of x all squared dx. And so basically the question is done, but we have to compute the derivative of this function, which looks like it might get a little bit ugly. So f prime of x. I have a product of two functions here, this exponential thing and that trigonometric thing. And so I have to use the product rule. I differentiate the first. So that gives me e to the -5x squared. I differentiate it with respect to the exponent, and then I multiply by the derivative of the exponent, which is -10x. And then leave the cosine alone. By the way, the parentheses aren't strictly necessary because it's clear by context that the 20 and the x both belong to the cosine. All right, next term, e to the -5x squared, and then I have to do the derivative of the cosine piece, which gives me negative sine 20x. So I differentiated with respect to the argument and got just a negative sign of the same thing, and then multiply by the derivative of the argument with respect to x. All right, and we'll see if there's some things that we can clean up. I can factor out a 10 from each term. It leaves a 2 in the second term, and then the e to the -5x squared is also common. And both of these are negative, so I'm going to pull the minus out too. Minus 10 e to the -5x squared. And yeah, I think I'm happy with that. And I'm left with x cosine 20x. And in this term, I pulled a 10 out of the 20, so I'm still left with a 2. So I have 2 and sine 20x. Okay, and then I'm supposed to square that thing. I'm not going to expand that. I'm just going to leave it. So I have my total arc length is the integral from -1 to 1. Square root 1 plus, I'm not going to write the minus sign because it goes away when I square. Okay, so I think maybe one additional point about this. I'm going to call this the answer. But one additional point I want to make is that this function is an even function. So I can tell it's even because if I evaluate f of -x, I can see that the x is just squared in this exponential. So my minus sign is going to go away. And then the cosine is an even function. So the cosine of the negative of an angle is equal to the cosine of the positive of the same angle. So this is just e to the -5x squared cosine 20x, which is equal to f of x. So f of x is even. That would allow us to clean things up just a little. I could just say that, oh, and you can tell in the picture this is true. that the arc length on the right hand side is exactly the same as the arc length on the left hand side because it has this y-axis symmetry. So if I wanted to get a little bit clever, I could start from 0 and multiply the whole thing by 2. In other words, I just got this side and then doubled it to get the total arc length, which is fair. All right, this integral would have to be numerically approximated. There's no way you're doing that symbolically.